Today's webinar is going to be over interpreting latent heat warning messages in Xchanger Suite. I'm Lauren Moran, and I work in engineering services, and I'm the manager of HRI's technical support group. The goals of this webinar are to identify the latent heat warning messages in Xchanger Suite and explain how the software determines latent heat and discuss its impact on the thermal design. We issue 3 warning messages regarding latent heat. In our earlier versions of our software, we noticed that it was calculating unreasonably high latent heat values. So in version 7.1, we started limiting the latent heat value to approximately around water's latent heat at vacuum conditions. And that's a fairly high latent heat value, so we thought this is a reasonable limit. In this message, we explain conceptually how latent heat is calculated, and we recommend checking the fluid properties. The other message that we issue is the negative latent heat. This message has been in our software much longer. Now, we don't actually use a negative value in the thermal calculations, but rather we throw this value out and use the previously incremented calculated value. The last message that we could issue regarding latent heat is the discrepancy in the specified value versus a calculated value. There are no errors associated with these warning messages. They are enunciated well, and these messages are good messages as it helps indicate continuity or ensure continuity in the fluid properties. The latent heat is used in our 2-phase correction factors. It's also used to determine the amount of contributions of the individual coefficients to the overall coefficient. You can see in the boiling methods, we use it both in the correction factor to the nucleate boiling coefficient and the convective boiling coefficient, similar with the condensing methods. Latent heat is also used in determining surface tension, assuming that the surface tension is not specified directly. The surface tension is used in a number of our 2-phase methods. Latent heat, like all other fluid properties, are important for good, accurate thermal ratings. There are 2 main causes of these types of messages. The first cause is a user-specified error. Notice the table on the right side. Now, it might not jump out at you, but there's a user input error. If you graph the fluid properties, you can quickly spot the issue. Here you can see that a decimal place has been moved over. The other common cause of this warning message, or these warning messages, are when you have small changes in weight fraction vapor over a temperature profile. I'll explain further why these results are sensitive to cases later, but let's first take a step back and look at some definitions before we get into the case study. Here are some basic definitions for sensible heat, latent heat, and enthalpy change. Sensible heat is the energy that changes the temperature, where latent heat is the energy that happens, or the thermal energy exchange, during a constant temperature process. Enthalpy change is the exchange of energy from 2 different thermodynamic states. So this could be between 2 incremental points on a heat release curve, or between the inlet and outlet of a heat exchanger. So Xchanger Suite assumes that any energy exchange that is not sensible must be latent, and that it is caused by the change of phase within the system. So here is the sensible enthalpy associated with the vapor phase and the sensible enthalpy associated with the liquid phase. This is the latent heat value, and you can see the delta Y term, or the change in weight fraction vapor term here. And that makes up the incremental or the enthalpy change that's being considered. So if you emailed us in technical support regarding latent heat, you would have seen that we essentially restate the warning message. But we give you this equation. Now this is the same equation that you saw previously, just solved for latent heat. The enthalpy is between two different points, and so is the weight fraction vapor and the delta T. The heat capacities are the average of those two properties between those 2 points, and so is the weight fraction vapor. In our standard response in tech support, we state that the latent heat is well defined for a pure component. You could take the saturated vapor enthalpy minus the saturated liquid enthalpy to determine the latent heat for a pure component. So here's the sensible heat associated with the liquid phase and the sensible heat associated with the vapor phase. And the difference between these 2 points make up your latent heat. Now, with a mixture, you can't subtract the saturated conditions to determine the latent heat. So you still have the sensible heat associated with the liquid phase when the phase is all liquid right here, and the same thing, the sensible heat associated with the vapor phase in the all vapor region. However, there is a temperature change over this same weight fraction vapor. So there's some sensible heating occurring in this region, so you could not subtract this point and this point to determine the latent heat. So what you need to do to determine it is to calculate the amount of sensible heat that's occurring in this region, and we can do that by using average conditions. So we take the average weight fraction vapor, the average vapor heat capacity, and the average liquid heat capacity, and come up with the sensible heating that's associated with the vapor and the liquid phase. And the difference there is the latent heat. Now, in our responses within tech support, we indicate that this calculation is very sensitive to small inaccuracies of the heat release curve. This is even more sensitive when the sensible duty makes up the majority of the total duty. We also note that hand calculations can be tedious for all the incremental values, and thermally, it may not be worth the effort as you can directly specify the latent heat for the calculations, which can allow you to ignore these error messages. So let's take a case to help highlight this issue. This is a stripper preheater where the kerosene liquid is exiting the bottom of a stripper column and is used to preheat the stripper feed from a separator. So here you can see on the shelf side you have single phase liquid being heated over a good temperature range. It's a typical AES heat exchanger single pass. The tube side fluid has a very small change in weight fraction vapor. The change in weight fraction vapor is about 0.01 in this case. It's occurring over fairly large, over nearly 140 degrees C. So it's got a large temperature range. Now if you ran this case, you would look at the overall results. You'd see that it's tube side limited. The shelf side's very healthy. You've got a good EMTD, and you've got a healthy over design. However, you would receive these two messages. Now, a side note, previously our software had a limit on how many warning messages that we could physically issue. When we hit that limit, you would have noticed a message saying that there's too many to print. So one of the things that we did is we limited the number of times we would issue these particular messages. So you would get you would see at least one of these messages. You would see at least one of these messages, and we limited to the very last time it was issued. In the future, we're going to, or in version 8, we were able to increase the number of times that we could, the number of messages that we could issue. So future versions will go back to issuing all these messages. So even if you only see one of these error messages, there could be multiple that we are not issuing. So let's go ahead and take a look at and do exactly what the warning message says. It says the latent heat has been limited to 2,500 kilojoules per kilograms, and it says to check the specified heat release curves and the vapor and liquid heat capacities. So here you can see that there is a user error specified in the results. If we correct this user error, you can see a much more logical trend in the liquid heat capacity. Now if we rerun the case, you could see that the results, the tube side coefficient does decrease. This makes sense considering the fact that we had a very high, over a factor of 10, liquid heat capacity for one of the increments. This reduced the overall overdesign from 21% to 18, a little over 18%. Now, if you go back to the runtime message, you would see these two messages are still being issued, except instead of increment 11 or increment 16, we're now seeing it at increment 11 for the second isobar. So let's continue to look at the fluid properties. Here is the heat release curve, and it's a plot of the enthalpy value with respect to temperature and the weight fraction vapor with respect to temperature. You can see that the weight fraction vapor does not significantly change. What we've plotted here is from 0.02 to 0.012. The version 8 feature where we've auto-populated the graphs makes these checks very easy in version 8. Well, there's nothing that I see that sticks out to me that indicates a problem, so let's keep on looking at the fluid properties. We're going to focus on the heat capacities next. Here's the liquid heat capacity with that corrected value. This trends very normally, very reasonable. The vapor heat capacity, there's pretty significant change over the vapor heat capacity. It decreases pretty rapidly, and if you recall, most of this fluid is liquid. So there is only just a small amount of vapor in this system. And so very likely it starts out as some hydrogen that's in that vapor phase. And as some hydrogen or hydrocarbons are vaporizing, it reduces that heat capacity down to what's probably more reasonable for a hydrocarbon heat capacity. I think this tends to be a pretty reasonable value. Ideally, knowing the system would be nice, but this is not something we're aware of for this particular process. But if you have compositional data, you could actually look at some of the composition data to determine what's the appropriate value. The one thing that the error messages doesn't tell you to do is to look at the back calculated latent heat values. You can see that the software did in fact limit the heat capacities, and so you can see kind of a cutoff here to 2,500 kilojoules per kilograms, as the warning message states. However, you won't see a negative value. Remember that we're going to throw out the value the negative value that we calculated and use the previously incremented calculated value. So here, now I did the detailed hand calculations, and so I could tell you exactly where the negative latent heat occurs and the excessive latent heat occurs. But also looking at the graph itself, you could kind of indicate where it might have occurred. When you see exact same points that might indicate that there are some negative latent heats in that position. But here was a negative, and we used this point, and then this and this one were negative calculated latent heats. So again, we used this calculated incremental calculated results. Then we have several good latent heats calculated, or I can say that they're reasonable latent heats. But then we hit an excessive latent heat, and we hit that, and we changed it to limit it to be 56 kilojoules per kilograms. The next one over, we hit a negative value, so we used the previous value. So instead of using a negative value or a small value, we used a previously calculated value, which was an excessive value. We got an excessive value again, and then a negative value, and so on and so forth. Now, really what this shows when you look at this graph, the way these latent heats trend and how they span from around 300 to over 2,500 should indicate that these back calculated values are not reliable and should not be used in the calculations. Ideally, you'd have a process simulator to generate the latent heats directly, and you can put that into your profile. If you don't have access to a process simulator, you could look at the composition, how the fluid is changing, and that could help you determine what an overall average latent heat. So if you knew some hydrocarbons were condensed, vaporizing, and then maybe water, maybe the latent heat would trend from around 300 to 600 up to a latent heat of higher values, like near 1,000 or over that. In this particular case, I was not aware of what the composition actually was, so I did do a hand calculation based on the entire temperature range. So I did an average white fraction vapor, so I did one step size, and to determine a latent heat, and that came up with a value of about 370 BTUs per pound. I inputted that into this case, and you can see the results further decreased. So considering how the latent heat was, a lot of the increments used this excessive value. Right here, you can see how the inputting a value of 370 would have decreased the tube side coefficient. Now, this case was very sensitive to latent heat, which is one of the reasons why I actually chose this case. But you can see it decreased it from 18% over design to 10% over design. If you go to the runtime message, you would actually see another message issued. You'd see all three of our warning message. So there's still an excessive latent heat calculated, a negative latent heat calculated, as well as now a discrepancy in the calculated value versus the specified value. But we state that the specified value is used in all the calculations, and that's the important thing for us to consider in the thermal rating. So hopefully this webinar has helped highlight the need for the error messages concerning the latent heat. This doesn't require removing these messages specifically from the program. Another lesson I hope that you learn is that you really need to look at the latent heat back calculated values. The sensitivity will be determined by case, but ideally you should always check or specify a reasonable latent heat or generate the latent heat from a process simulator. There are ways that we want to look to improve our software in future cases. Having quite a few warning messages is not the ideal situation. So some possible software revisions that we're considering is maybe taking larger step sizes when we see these excessive and negative latent heat values. Or we may consider determining an overall average latent heat by calculating the incremental sensible heat over each increment, summing all those and coming up with an overall average latent heat. Those are just two possibilities that we're considering for software revisions and calculating the latent heat. This concludes what I have to say, and I appreciate everyone listening.